Hi, in this masterclass, I'll be covering some of the new RBD-related features in Houdini 17. As an outline, I'll be starting out with constraints, looking at the new soft constraint, along with some useful new options on the glue constraint. Then we'll be moving into SOPs and taking a look at the new Convex Decomposition SOP, as well as some useful new utility SOPs like Extract Centroid, Extract Transform, and some handy new options on the Attrib Promote SOP for working with RBD objects. Finally, we'll be looking at the new fracturing tools, including version 2.0 of Voronoi Fracture and a new Boolean Fracture SOP, and then the higher level material-based fracturing toolset that we've introduced in Houdini 17. All right, so we'll start off by taking a look at the soft constraint, which is a new constraint type that we've added for Bullet in Houdini 17. So the soft constraint does act like a spring, so it's applying a force that's proportional to the distance between the two anchor points, and you can also have some damping, but it does have a lot of differences in its behavior when you compare it to the normal spring constraint, so we'll be taking a look at some of those changes. For advanced users who might have been familiar with doing this in previous versions, it's actually kind of similar to the effect you might get by configuring some of the more advanced parameters of the hard constraint in order to make it behave in a softer manner. But you'll find that the soft constraint is a lot more straightforward to deal with and easier to tune than trying to tweak the hard constraint to give you a softer looking behavior. So in this setup here, I've just taken a bunch of spheres, scattered them through a box, and then used connect adjacent pieces to create a whole bunch of interconnected constraints between them. And then I've just configured them to be set to use the new soft constraint and also affect both position and rotation. And so then here I've just got a normal constraint network set up using the soft constraint just at its default values for now. And if we press play, we'll see that we get kind of a nice bendy and springy looking effect for our object. So on the parameters for the soft constraint, there's a few of the usual parameters that you're probably familiar with from other constraint types. So there's the rest length parameter here, and then there's the option to override the number of constraint solver iterations if you wanted to use something different than the default value on the bullet solver for these constraints. And then there's also the option to disable collisions between the pairs of directly connected objects. The other two parameters are really the important ones for controlling the look of the spring. So we have a stiffness parameter and a damping ratio parameter. And if you compare this to the spring constraint, it has a strength parameter and a damping parameter. And these have some subtle differences between them. If you're familiar with physics, the strength and damping parameter on the spring constraint correspond to the spring constant and the damping coefficient that you would be familiar with from a damped harmonic oscillator. And in the case of the soft constraint, the stiffness is the frequency of the spring, so the number of oscillations per second, and the damping ratio. Really, the important thing here is that the stiffness and damping ratio parameters are mass independent. So they're really just specifying the look of the spring. And so if I change the mass of my objects around, or I have a bunch of objects with varying masses, I'm still going to be able to get the same look to my soft constraint, which isn't the case with the spring constraint, where those spring coefficients and so on are very dependent on the masses of the objects. So in this case, if I take my objects, which just had the default density, and I lower that quite a bit, and then resimulate, you'll see that we actually get a very similar look to the objects. And so this makes it a lot easier to deal with for destruction type simulations where you've got a bunch of fractured objects that have totally different sizes, some really tiny objects in there, and you want to be able to get a consistent look to your springs throughout the simulation. And then if you go back and refracture your object a little bit differently, the look isn't going to change very much on you. And so you can spend a lot less time tuning your constraints. And so just as a point of comparison here, if we were to wire in this spring constraint instead and just update the data name to soft and give it a moderate strength, it's going to be looking very different as we change the mass of the objects around. So in this case, it's somewhat stiff. And then if I go back and reset my density to the default, it's going to look quite a bit different. And so now it's acting a lot softer just because the mass of my objects increased quite a bit. So let's change that back to the soft constraint for now. So getting back to the parameters, the stiffness parameter on the constraint is fairly straightforward. So a larger value just gives you a stiffer effect. So if I make this really small and then resimulate, we'll see that the constraint's allowed to stretch quite a bit and it doesn't recover very quickly. And then as I increase it further, so maybe to 100, we'll see that it's starting to get a much stiffer look. And then as I increase it even further, it just gets stiffer and stiffer. And so as this value goes towards infinity, it'll essentially end up approximating what a pin constraint would give you. And so just like the pin constraint, one thing to keep in mind is that if you're increasing the stiffness further and further to make it almost like a rigid constraint, and you're still seeing a bit of give in there, like in this case, when that impact first happens, we'll see that it does bend just a little bit around the middle. One thing to keep in mind is that if you're seeing that, even though you think that your constraint should be a lot stiffer, you might need to be increasing the number of constraint solver iterations. So if I crank that up in this case, we'll see that we do get a somewhat stiffer looking effect and a lot less bending at that case. So just one thing to keep in mind is that you might need to also increase the number of constraint solver iterations if you're trying to get stiffer looking constraints. And so then the damping ratio is the other parameter. And this has a bit more of an interesting meaning to its scale. So a value of 0 corresponds to no damping. So you'll see that we get a very, a lot of oscillations showing up. In this case, once it bounces back, we'll see some oscillations happening. And then as we increase that towards 1, we'll reach what's called critical damping when the value is 1. And this is where you have just enough damping to avoid any oscillation as it's coming back to its rest position after it's been stretched. So this is just enough to give you kind of a springy look, but without any bouncing afterwards. So you'll see that here, that once it gets back to its rest position, we're not getting any more oscillations after that point. And then as you increase it past 1, you just end up with an overdamped spring. And so increasing this further will just give you a progressively more damped effect. And there you go. So one thing to keep in mind is that this is really just like any of the other constraint types that Bullet supports. So during the simulation, the solver is also going to be outputting the usual attributes that we're familiar with, like the force attribute, torque, distance, and angle, that are just giving you some information about the state of the constraint in the simulation. So like how much force the solver was applying in order to enforce that constraint. And so of course we can use this to break constraints or do whatever we want during the simulation. So in this case, I'll just maybe make the stiffness a little bit higher for this example and reset the damping back to 1. So then if I turn on this solver here, which is just operating on the constraint geometry subdata for the constraint, we just have a simple wrangle here that's checking what the torque value was that the solver outputted. And then if it's greater than our tolerance, which in this case is 70, we're just going to delete that constraint. And so we can get a nice braking effect as the simulation goes on and some impacts occur. So as I mentioned before, there are also some other differences with how the soft constraint is solved by Bullet compared to the spring constraint, aside from just the differences that we were talking about with the stiffness and damping ratio versus the parameters on the spring constraint. And so we'll take a look at this here in sort of a more isolated case to make it a bit more clear what's going on. So in this case, we have something that's kind of a bad scenario for the old spring constraint, where you have objects that have a very small mass, and then we have relatively few substeps on the solver. And then we've got a spring that's relatively strong, but doesn't have any damping whatsoever. So we're going to get a fairly highly oscillating spring. So if I press play here, what we'll see is that there's actually a fair bit of energy loss, even though we don't have any damping on. And this is something that you'll see with the soft constraint if you have relatively few substeps. So if I increase this even lower to just 1 substep, we'll see that the energy loss is fairly rapid. But then as I increase the number of substeps, we'll see that it behaves a bit more like what we'd expect with not having any damping enabled. And so this is really the trade-off with the soft constraint. The method that the Bullet solver uses to solve the soft constraint springs is different than the normal spring constraint, and it's guaranteed to be stable. So the soft constraint will never blow up on you, unlike the spring constraint, which could very easily blow up if you had small masses for your objects or you didn't have enough substeps. But the trade-off with that is that you may see some artificial damping being introduced if the number of substeps isn't very high for the soft constraint, and that's what we were seeing here. As we increase the number of substeps, we saw less and less of this artificial, unexpected damping that was being introduced by the solver. So what that means really is that if you have cases where you want to have springs that oscillate quite a bit and have very little damping, you might still want to use the traditional spring constraint because it'll let you get that look without having to crank up the number of substeps as high. But otherwise, in most cases, especially for destruction type simulations where you want to do some bending and then breaking, you're already going to be using some damping anyways. And so if there's a little bit of extra artificial dampening that gets introduced by the solver, that's a perfectly good trade-off because you're going to be able to get much more stable results with the soft constraint. And it's also quite a bit easier to tune, especially when you have objects that have varying masses. So the recommendation would be to use the soft constraint in almost every situation, unless you find yourself needing to have very highly oscillating springs and you want to avoid having to increase the number of substeps. So in this setup here, I've got a pretty straightforward glue setup. I've just fractured this wall into a bunch of pieces and set up glue constraints between all of them. And then I've got a collider that's coming through and breaking some of those pieces off. But what we'll see here is that the impact doesn't end up propagating very far. You just kind of get a few pieces around the impact location that are breaking off, but it's not really traveling much farther in the glue constraint network and breaking off some pieces that are further away, which is what we might want if that's the effect we're looking for. So I'll just start off by doing a quick review of how the glue parameters work and are handled by the solver before talking about the new changes. So as the simulation goes on, what the solver will do is it'll take the impacts that occur and then take the impulse from the collision response and record that as a primitive attribute on the glue constraints. So in this case, if I look at the constraints, as the simulation goes on, this impact attribute will get some values added to it by the solver based on how strong the collisions were. And so then if that impact value gets to be larger than the glue strength, that will cause the solver to break the constraint, and then the piece will end up moving on its own. And then if the impact value wasn't high enough to break the glue, that's where the half-life starts to come in, which just decays this impact value over time. And so what this really is for is so that if you have a bunch of fairly small impacts that keep repeatedly occurring over time, it won't necessarily cause the impact value to, accumulate high enough to break the glue in case you don't want those sort of small repeated collisions to cause any glue bonds to break. And then the other thing that happens is the glue impulse needs to spread throughout the glue network so that other pieces that are farther away from the impact location can be broken off. And so that's where the propagation rate comes in. So what the solver will do is it'll do a number of iterations of diffusing or spreading that glue impulse throughout the network, and it does that according to this propagation rate. So if the value is 0, an impact against one of the objects won't spread at all to any of its neighbors. And then if it's set to 1, it'll be spread evenly to all of its neighbors. So it'll kind of diffuse smoothly throughout the glue network and still conserve the total amount of impulse that was added into the glue network. And then the solver will do a certain number of rounds of iterations of doing this propagation. And so this is really what controls how far and how rapidly the impact can spread throughout the glue network. So previously in Houdini 16.5, the number of rounds of propagation that were being done was a global property of the entire constraint network. So it just did a fixed number of iterations of doing this for all of the constraints in the glue network. And so if you wanted to control this, you had to control it with a detail attribute on the constraint network because it applied to all of the constraints globally. And so we can see that effect here. If I turn this on in my attrib create SOP and I set up this detail attribute called propagation iteration and set that to 10, let's say, instead of the default of 1, then if I look at the simulation, we'll see that the impact travels a lot farther throughout the glue network and more pieces are broken off. There are a few changes to this that we've made in Houdini 17. So one, which is a little bit harder to demonstrate quickly here, is that there were a lot of performance improvements done to the glue propagation stage in the solver. And so there's quite a bit less overhead now to increasing the number of propagation iterations. So you can increase that a lot higher without having as much of a performance penalty. But more importantly, it's been changed to be a per primitive property rather than just a property of the entire constraint network. And so now it shows up on the glue constraint as the number of propagation iterations. And so this is kind of like what you would see on the other constraint types that Bullet supports that have an option to override the number of constraint solver iterations for the constraint types that aren't glue and are more like traditional constraints like springs. And so this kind of behaves the same way. So a value of -1 means just use the default value. So in this case, that means use that detail attribute if it exists for backwards compatibility, or just use the default value of 1. But then if we want to override that ourselves, we can change it to a non-zero value. So if I change it back to 1, then we'll see it's like what we were seeing before, where it doesn't propagate very far. And then if I increase that to 100, let's say, the impact will propagate quite a bit further and break off a lot more pieces. The other neat thing that this lets us do, aside from just having this option be a lot more discoverable and easy to set up, is that we can also now vary it per constraint. So I'll just reset this back to 1. And then if I go back to SOPs and I'm looking at my constraint network, I've got this attribute create I've set up here to set up the propagation iterations primitive attribute to override the propagation iterations parameter on the glue constraint. And so if I, for example, select a group here and I'm going to set the propagation iterations attribute to be a value of 100 for these constraints that are on the right side and just the default of 1 on the left side, we can actually get some pretty interesting effects from doing that. So if I press play, we'll see that we've now got kind of an interesting shape to how the impacts propagate through the glue network. So this can be kind of a handy tool, aside from just changing the strength values in certain parts of your glue network to get some interesting breaking effects. Let's take a look now at some options for setting up proxy geometry for concave objects in Bullet, which is a problem that tends to show up a lot in RBD simulations. So there are a few different ways to go about this. So one option that you always have with concave objects is just on the Bullet Data tab to pick the concave geometry representation. But there are a few downsides to this. Probably the main one is performance. It works pretty well if you have maybe a couple of colliders that you're trying to bring in, but if you are trying to do this for a lot of fractured pieces that have concave bits to them, it might not scale very well. You're generally much better off with Bullet using things like convex hulls, spheres, boxes, and so on, that it's able to deal with much more effectively. The other problem that can also come up with the concave representation is that Bullet basically just treats it as a whole bunch of polygons. There isn't really any notion of inside or outside. And so this can cause some trouble if you have fast moving objects, let's say, where from one subset to the next, an object goes from outside to inside the object. Because Bullet lets you collide against both sides of the triangle, it kind of treats it as though it was just an open surface that you can collide on either side. You can end up having objects getting stuck on the wrong side of the object and not getting pushed out when you intended them to be. And so it tends to be a lot better to use things like convex hulls or spheres where Bullet has a very well-defined inside and outside so that it can resolve any penetrations that happen from one substep to the next. So one approach that you have for setting up proxy geometry that I wanted to show quickly, this is something you can do in 16.5, is using the VDB to spheres approach. So in this case here, I'm just going to take this torus and shatter it into a few pieces, but we still have each of these pieces are still somewhat concave. And then we have this option on the rigid body shelf to set up an RBD sphere proxy. So I'll just select my geometry. So what this did for us, let's take a look back at the setup, is so after our original source geometry that had been fractured into a few pieces, set up a for each loop going through each of these pieces, and then it uses VDB from polygons to convert that geometry into a volume. And then it uses the VDB to spheres SOP to fill up that volume with a whole bunch of possibly overlapping spheres. And so this is what we're going to use in Bullet as our proxy geometry. And the nice thing here is that spheres are really efficient for Bullet to deal with. It's very easy to do collision detection for spheres. They're very lightweight. And so this can work pretty well as a proxy representation. It can be a lot faster than concave objects or even convex hulls. And so then we have the rest of our for each loop that's set up the proxy geometry for the rest of the pieces. And so if we look at the geometry here, we still have a name attribute just like before. So we have piece 0 through piece 9, but instead of each piece containing a bunch of polygons, each piece now just contains a whole bunch of spheres. So if we look at our exploded view, we've still got the same number of pieces that we had before. Just now each piece consists of a bunch of spheres. And so then if we send that into DOPS, the only thing that we really need to be careful about setting up on the DOPS side of things is our collision shape. So using the default settings, so just the default convex hull, what Bullet will do is take the geometry of the entire piece, so in this case a whole bunch of spheres, and it'll compute the convex hull of all of that. And so we'll see here that it's kind of undoing all of this clever work that we just done to try to set up a nice proxy representation. And so it's still giving us kind of an ugly, overly large collision shape. So what we can do instead is turn on this option to create convex hull per set of connected primitives. And so what this will do is for each piece, it'll look at all of the sets of connected primitives. So in this case, because we just have a whole bunch of spheres, none of them are connected to each other. But in the case of polygons, it would be each set of connected polygons. So it'll go through each of the sets of connected primitives. So in this case, every single sphere, create a collision shape for that. So just a bunch of sphere collision shapes, and then assemble all of those into a compound collision shape that it'll use for the entire piece. So if I turn that on and turn off the display geometry, we'll see that it's now just basically directly using our spheres as a compound collision shape for each of those pieces. So I'll just add in a ground plane to make this a little bit more interesting. And then if we press play, we'll just go back into DOPS. I was looking at the wrong geometry. We'll hit play, then we'll see our simulation working nicely with the proxy geometry. And so then afterwards, what we need to be able to do, of course, is transfer the motion of those proxy pieces back onto our original pieces that we had built our sphere representation from. So what we can do here is the typical workflow of taking the DOP import SOP, which is set to create points to represent objects. And what this does is for each of the pieces in our simulation, it gives us a point that has its position, orientation, and so on. It's transformed from the simulation. And then we can use the transform pieces SOP to take our original pieces and then apply the transform from the simulation for each of those pieces. So now we can just apply that motion onto our high-res geometry. So this works pretty well. Using spheres is very efficient. So this can be a pretty good performing way of dealing with concave objects, but it does have a couple of downsides. One is that if your original geometry had flat surfaces and hard edges, that kind of gets lost if you're trying to use a proxy representation that's made up of a bunch of spheres, because it kind of just rounds out the shape of the object. And so you can kind of see that in this example here, where some objects do kind of roll a bit more than you might expect them to be. So it doesn't necessarily hold up as well for foreground pieces, but it can be a pretty effective technique for objects that are more in the background. The other thing to be aware of too is that there's a couple of things that you need to always have to tweak with this process. So one is you're converting the geometry into a volume. So if you have more complex geometry with some small features, you might need to be tweaking the voxel size to not lose any parts of the geometry that you care about. If there's like really thin parts, for example, in the space between fingers on a character, things like that. And then you also need to tweak some of the VDB to sphere settings to control how many spheres you want, what the minimum maximum radius is, and so on. So there's a little bit of tweaking that you have to do, but this can be a fairly effective technique. So as an alternative to the sphere packing approach, we've added a new SOP in Houdini 17 that gives you another option for how to set up the proxy geometry for concave shapes, and that's the Convex Decomposition SOP. And so the idea with this SOP is to take the geometry and cut it up into a bunch of different segments so that each of those segments is convex or close enough to being convex given some tolerance. And then we can use that as our proxy geometry as a compound shape in DOPS. So instead of having our proxy geometry made up as a bunch of spheres that approximate the shape of the original concave piece, we'll instead take, say, a dozen convex hulls that together as a compound shape give us a good proxy representation. So let's take a look at what this looks like on the squab, which is a nice example to work with since it's pretty concave. So here, the main parameter is the max concavity, which is basically our tolerance for how close each of these segments can be to being perfectly convex. So you probably want to leave this somewhat high so that you don't get too many pieces. If you have a really bumpy piece of geometry, you might end up needing a ton of convex hulls to make a perfect representation. So in this case here, if I turn on this visualizer button, we'll see each of the pieces that got produced. And so if I set the tolerance really high, nothing really happens because we're allowing there to be a fairly coarse representation. And this is basically the same result as just taking the convex hull of the entire geometry. But as we reduce this, we'll start seeing more convex hulls being produced, but they're a better fit to the original shape of the geometry. So this is really the main parameter that you need to deal with, controlling how accurate you want the proxy geometry to match the original geometry, but without producing way too many pieces to make the representation inefficient. And then there are a couple different options for what geometry you want to get produced by this SOP. So the default behavior is to output the actual convex hulls. So you're basically seeing exactly what Bullet would be using as its representation in DOPS. And then there's an attribute called segment by default that gets output to identify each of these pieces. And then the other option you have is to output the actual original segmented geometry. So we can see here, if we do an exploded view, this is just the original geometry, but with all of the cuts that have been made by the Convex Decomposition SOP. So we'll see that it's been sliced up into a bunch of different pieces. And then just like before, we do have a segment attribute, but then we also have a group that's also added for the interior faces that got produced by any of those cuts. So this option can be useful just for kind of visualizing what was happening on the original geometry, or using this as sort of a generic SOP tool, but probably in most cases you'll want to output the actual convex hulls because you can just send those directly into Bullet. It's already the same geometry presentation that the solver would be computing anyways. So there are a couple other useful options here. One is this piece attribute option. And so this SOP actually has the option to run over a whole bunch of existing pieces. So over here, I've taken the squab and pre-fractured it. So I've already got a bunch of different pieces, some of which are concave and should be decomposed a bit further. And then if I turn on the piece attribute option, the SOP will run over each of those pieces individually and then decompose them if it needs to based on the concavity threshold. So here I've basically got the convex hulls for sort of my original geometry. And then as I reduce this, some of the pieces that were concave are getting divided further into a few different convex segments. And so if I look at the exploded view here, if I explode by name, we'll see that just like before with VDB to spheres, we still have the same number of pieces as before. So the name attribute before we had 24 different pieces, and then afterwards we still have 24 different pieces. Just now, each of those pieces consists of a few different disconnected segments for each of those convex hulls. And then the segment attribute lets us identify each of those segments individually from each other. So if I switch my exploded view to work by, split them apart by the segment attribute, then we can see each of those segments individually. But Bullet will still be seeing 24 pieces just like before, but each of those pieces is made up of a bunch of different disconnected convex hulls. There are a couple other more advanced options just to quickly mention. So one is this treat as solid option. And so to demonstrate this, I'll just make my geometry open. So if I take the squab here and say delete one of these pieces, oops. There we go. So if I delete one of these pieces and I had left this option off, it's easier to see with the segmented geometry. So if I had some hollow open geometry here, what the SOP will do is basically treat it as though it was a hollow shell. So you'll see here that it didn't fill in the interior when it made any of its cuts. And then if I was going to decrease this concavity, it would continue cutting this as though it was a hollow shell. So it keeps trying to decompose further until these little shells here are close enough to being convex. But what I might want to do is have the option to kind of ignore any small holes in the geometry. And so that's what this option will do. It kind of implicitly does a polycap on any holes in the geometry. So if I turn that on, we'll see that it basically behaved as though the hole wasn't really there. And so we're still filling in the interior surface, and it's not trying to further decompose any of these solid chunks. And then finally, the Merge Nearby Segments option lets you deal with the case where your original geometry already consisted of a couple different disconnected pieces. So I'll show that here just by setting up a somewhat contrived example. So in this case, if I had my original squab, and then I also had, say, a box that was adjacent to it. So here I'll just make this box a little bit smaller and then bring it up like that. So if I were to send this into the Convex Decomposition SOP, what it normally does is it just looks at all of the individual segments that already exist in the geometry. And then if any of those are concave, it'll start to decompose them further. But if they're already convex within the threshold, then it won't really do anything. So we'll see here, even if I set my tolerance super high, it didn't actually like merge those two segments together or anything like that. It just decided both of them are already convex. It doesn't really need to do anything further. So what this Merge Nearby Segments option will do is allow the SOP to do more searching to figure out if it could come up with a larger convex hull that can enclose both of those segments and merge them together, but still satisfying this concavity threshold. So if I turn that on, now we just have a single convex hull that wraps around both of the segments that we had in our original geometry. And then as I decrease the tolerance, it may or may not decide to merge those together depending on what it thinks it's able to do, given the concavity tolerance. So this can be a handy option if you have your input geometry already consisting of a bunch of disconnected pieces, but you want to give the SOP the option to give you a larger proxy shape that represents the geometry as a whole. And so then finally, just like what we had with the torus, we still have a shelf tool that will set up all of this for us. So I'll just take a quick look at that. So going back to the original squab, if I use the RBD convex proxy shelf tool, this does kind of the equivalent of what the RBD sphere proxy shelf tool did for us with the sphere packing option. And so if we jump back to SOPs, we'll see that what it did was it just took our original source geometry, ran it through the Convex Decomposition SOP with the piece attribute option turned on, so you could have already pre-fractured your geometry, and then sent that into DOPS. And just like before, we turn on the option to create a compound collision shape. So we're using the convex hulls that we've already computed using the Convex Decomposition SOP instead of just wrapping it all in one big convex hull. And then back in SOPs, after the simulation, we're doing the same DOP import as points and then transform pieces set up as before. So the Convex Decomposition SOP can be a pretty handy tool if you don't want to use the sphere packing approach and you want to be able to just very efficiently deal with any pieces that happen to be concave. So with this piece attribute mode, it's really easy to just run it over all of your fractured geometry afterwards. It's very fast at detecting pieces that already are convex. So if you just happen to have a few, a relatively small number of pieces that end up being concave after your fracturing, it's very efficient at just identifying those pieces and dividing them a bit further if it needs to. So next up, we'll start looking at a few of the SOPs that are either new or improved and are useful utilities for common things that you end up doing a lot with rigid bodies. So first up is Attribute Promote, which of course is not a new SOP, but it's got a pretty useful new feature in it that's very handy for a lot of things that you're dealing with fractured geometry. So as an example here, I've just got some geometry that I've fractured here with some small pieces and some large pieces. And one thing that you might want to do is find pieces that have a small or a large surface area so that you can maybe delete tiny pieces or something like that. So what I've got so far is just a measure SOP to compute an area primitive attribute, and then just a simple color visualization for the area. So we can see some of the pieces that have a small surface area being colored a little bit differently. So if I want to sum up the total surface area of every piece, what I probably would have done before was a for each loop. So I would do a for each named primitive loop running over each of our pieces. And then inside that loop, I would do an attribute promote to sum up the area attribute from all of the primitives that are in that piece, and then promote it up to detail, change this to sum. So now we've got a detail attribute with our total area for the piece, and then I'd have to promote it back down from detail to primitive. So detail to primitive area. Average doesn't matter in this case, but I could just make it first match. And so now if I look at that, then we've now got, as I increase the range on this visualization, we've summed up the area for each piece, and we can see the pieces that have a large surface area and a small surface area. So this is okay, but it does take a fair bit of work. We've got to set up a loop and use a few different attribute promotes to do something that's a fairly common task. So there's a very handy new option on attribute promote in Houdini 17, which is the option to use a piece attribute. And so what this will do is for each of the pieces in the new class, so based on, let's say I'm promoting from point to primitive, and I'm doing this based on a piece attribute, it'll take a look at all of the primitives that share the same value of the name attribute, and then grab all of their referenced points, and then do the promotion operation to, sum up the attribute or average it or whatever, and then write it back out to all of the elements of the piece at the primitive level. So let's take a look at this here. So in our case, we're actually trying to sum up a primitive attribute over the entire piece. So we'll set the original class and the new class to both be primitive, and then we'll turn on piece attribute. We already have a name attribute set up on our geometry, and then we'll use the area attribute and then just sum it up. So now you'll see that we've got an area attribute that has been summed up over all of the pieces, and if we change our visualization over to that, we got the exact same result. So this is a pretty handy option. It saved us quite a bit of work from before and ends up being quite a bit faster in practice as well. We'll take a look at a couple of other examples. So in this case here, we'll look at promoting attributes between different classes. So in this case, I've just got some fracture geometry that has a bunch of polygons on it, and maybe I want to visualize how far away each of the polygons are from the center of the object. So what I could do for that is do an attribute promote, and I'm just going to sum up or average the point positions for all of the pieces, and then visualize how far away each primitive is from the average point position in its piece. So in this case, I'm going to take the point position, so my original class is point, going to promote that up to primitive, but do it per piece. So based on my name attribute, and average is what I want. And then I'll just change this to average P, let's say. And then if I do a simple wrangle, I'm going to be running over primitives and looking at this average position. So I'll just set up an attribute called distance, which is just going to be the distance between at P, which for primitives is just going to be the average position within that polygon to the average position of the entire piece. So now I've got this distance attribute, and then I'll just set up a quick visualizer. This is a handy new feature actually in Houdini 17. So from the info window for a SOP, if you click on one of these attributes, it'll actually set up a visualizer right there for you. So you can avoid a lot of extra work setting that up. So now you'll see we're visualizing primitives that are very close to the center of their piece versus primitives that are a lot farther away from the average point position. And then finally, let's do one more example, just working at the point level. So in this case here, I've taken a whole bunch of points and used the cluster point SOP to just divide them into a bunch of different clusters. And let's say I want to do something interesting based on how far each point is from the center of its cluster. So in this case, I can just promote the point position per cluster and figure out the average position of that cluster. So I'm promoting from point to point, but based on the piece attribute cluster and averaging out those point positions and then writing that out to a new attribute called cluster center. And so then if I just do a simple wrangle, I can scale the points in this case based on their distance from the center. So if I adjust this, we can do some interesting effects like moving points towards the center of their cluster and further out and so on. So this new option ends up being pretty handy. It's nothing you couldn't do before, but it saves you quite a bit of work in a lot of common scenarios. So it's good to keep this in mind to simplify your work in the future. So related to what we were talking about right now with attribute promote, one thing that comes up quite a bit is finding the location of the center of a piece. And this, in particular, this happens a lot with constraint networks where you're often trying to generate a point at the center of each piece and then join them all together with polygons to represent the constraints. So there were a few approaches to do this before. Definitely you could use a for each loop or something like that if you wanted to, but the most common shortcut before was taking advantage of the pack SOP, which has an option to create a pack fragment primitive for each piece with one point attached to it, and then the point would be located at the centroid of the geometry. And so if you then just did a delete geometry but keep the points operation, you'd end up with one point per piece that's at a fairly reasonable location. The way that it computed the centroid on the pack SOP, though, was just based on the bounding box of the geometry. So depending on the shape of your object, that might give you something kind of far away from where you'd expect it to be. But generally, this was a pretty fast and easy to use approach, so it was done quite a bit. The other option you have, of course, is using what we just showed with attribute promote, so just computing the average point position of the piece, which can be a bit closer to the center. The one downside with this approach, though, is that it's very sensitive to how points are distributed on your original geometry. So if I take this divide SOP here, which is set to just do a bricker operation on one of the faces, if I turn that on, we'll end up getting our average being very biased towards this one side of the object just because there's so many more points there. So this approach is a little bit problematic sometimes. So in Houdini 17, we've actually added a dedicated SOP for this with a lot of useful options to make this very easy to do and also a lot more accurate. So this is the Extract Centroid SOP, and so by default, it's set to run over each piece. So if I delete this blast SOP, we'll get a point at the center of each of those pieces. And then it has a couple different options for what method to use to compute the center, and I'll look at that in a second. And then by default, it'll output 1 point per piece. So one option it does have for the method is the bounding box center, and this matches the pack SOP exactly. So you can use this to replace that method if you wanted to. But the better option that it has is to compute the actual center of mass of the geometry. And this matches exactly what the bullet solver would do when it's computing the center of mass of that piece. So this approach is a lot more accurate. It doesn't get thrown off by having a lot more points on one side of the object or the other. It's computing the actual center of mass where you'd expect it to be. So this generally gives you a point that's closer to where you would want for things like constraints. So it's a little bit more reliable to use than the bounding box if you're expecting the point to actually be more towards the center of the geometry, even if you have kind of an odd shape. So there are a couple other options to mention here. So by default, you can output points, and you have the option to transfer attributes from the source pieces onto those points. The other option you have, though, is to actually output the original geometry, but add an attribute with a particular name. In this case, centroid is the default. So this is handy for just computing the attribute and then letting you do stuff with it on the original geometry. And then you also have the option, instead of running over pieces, to run over the entire geometry. And so in this case, the attribute mode will actually add a detail attribute with the location of the center. And then if you are outputting points, it'll just give you one single point with the position of the center of the geometry. So this is a pretty handy utility just to reliably get points at the center of each piece and also simplify things, since it handles attribute transfer and things like that pretty nicely. And you can also generate the center of mass location on your original geometry if you don't need points to be created. So the next SOP we'll look at is the Extract Transform SOP. So this is actually a SOP-based version that we've added of the Extract Transform object, which you may or may not have used before. So the idea with this SOP is to make it easy to extract a rigid transform from geometry that just has changing point positions and appears to be deforming. So we'll find that this ends up being a pretty handy utility for setting up animated colliders for bullet and things like that. So in this example here, I've just taken some fractured geometry, and then I've just used a couple of transform SOPs to just apply some rigid transforms to the geometry. So something like this. And then we'll notice that all we have is just a bunch of changing point positions. So this is kind of like if you got a geometry sequence coming from some external application and you're trying to bring that in as your collision geometry. You just have a bunch of changing point positions over time, even though those point positions are actually just describing some rigid motion. So if we wanted to bring this into bullet directly, as is, we'd basically end up having to use deforming static objects rather than animated static objects. If we tried to use animated static objects, what we'd see is that if we look at the transform intrinsic on these packed primitives, nothing changes over time. And this is because the packed primitives transform is not changing. It's just the input geometry that's getting packed is changing. And so there's deforming geometry inside of the packed primitive. So if we tried to use this as bullet and had set it up as animated static objects, we'd see that nothing really happens because bullet can't pick up any motion. And so the objects just activate when I told them to activate, but they didn't really get any animation. So instead, I would have had to change this to deforming, which would work, but the downside with this is that bullet would be recomputing collision geometry on every frame, which isn't very optimal if I was dealing with some heavier geometry. So what we want to be able to do is extract that rigid motion from that geometry that just had changing point positions, and then apply that to our packed primitives so that they have an animated transform. So let's take a look at that here. So in this case, we're going to use our new SOP, Extract Transform, which takes two inputs. One is the reference geometry and one is the target geometry, which need to have the same number of points, and then it tries to figure out the best fit rigid transform that maps points from one to the points to the other. So in this case, I'll take the geometry from the first frame, just time shifted, and then I'll use my second input as just the current geometry at my current frame. And then extract transform will run, it has an option to run per piece or for the entire geometry. And then it'll find the best fit translation and rotation to transform the points from the reference geometry to the target geometry. And the output from this is actually just a bunch of points. And the format of this will probably look familiar to you from earlier when we were using the DOP import SOPs create points to represent objects mode, which gives us the same sort of output. So we have points that have a P attribute, orient attribute, and pivot attribute that are describing the transformation, along with the name attribute in this case because we were extracting per piece. And so what we can do with this is feed it into transform pieces, and we can apply that transform to any geometry that we want. So in this case, I'm going to take the geometry from the first frame, run it through a pack SOP. So now I have 10 pack fragment primitives. And then if I apply this transform from these points through transform pieces, we'll see we've got the motion that we want. And in particular, the packed primitives geometry, the contents of the packed primitives geometry isn't changing because we're just building this from the first frame's geometry. But if we look at the transform intrinsic, we're now getting an actual rotation in our transform of the packed primitive. So if I was going to send this into Bullet now, then we can just use our animated setup and set up animated static objects, and Bullet will pick up those transforms and apply those to the static objects, and then we can do our transition successfully. So this makes it a lot easier when you're working with external geometry sources and things like that to extract rigid transforms and apply them to packed primitives so that you can take advantage of animated static objects in Bullet rather than deforming static objects, which end up being a lot more efficient. I'll show another example just to kind of show some of the behavior of a few of the other options. So I'll just use the pig head here. Turn off the point display, and then I'll just use a transform SOP, let's say, to set up the target geometry. So I'll move this over a little bit, rotate it, and so on, and then put down an extract transform SOP, and then transform pieces. So we'll see what the effect is when we transform the original reference geometry. So in this case, because I just did a rigid transform translation and rotation with the transform SOP, the original geometry, when I apply that transform to it, will exactly match what my target geometry was. But let's say, to make things interesting, I had some different scaling or some distortion on the geometry. So now if I use extract transform to extract the best fit translation and rotation, we'll see that the reference geometry, when I apply that transform, doesn't match up with the target geometry. And it can't in this case because there's no way to just translate and rotate this geometry and have it match this geometry that was scaled. But it does do the best job that it can to make things line up as closely as possible. So there's one option on the SOP that lets you get a measurement of how successful this was, and that's this distortion attribute option. And so what this will do is give you a measurement of how close the geometry matches up with the target geometry, how much distortion there was. So larger values mean it wasn't as good of a fit. So in this case, we have a somewhat small distortion value because some of these points match up, but some of the ones near the ends don't quite match up. But if I had gotten rid of that scaling, then we'll see that the distortion attribute is essentially 0, like 1e minus 6. So that can give you a useful measurement of how successful or how rigid the deformation actually was. The other option that you have is, instead of just extracting the best translation and rotation, you can also extract the best fit translation, rotation, and uniform scale. So this will add a p-scale attribute into the output point. And then if I did have some scaling, then this allows the geometry to itself be scaled a bit further to match up with it. So in this case, where I'm uniformly scaling the target geometry, it's able to find a best fit uniform scale that also helps the reference geometry line up with it. So now we'll move on to talking about the fracturing tools, starting with Voronoi. So in Houdini 17, we've introduced a new 2.0 version of the Voronoi Fracture SOP, which has a number of changes and improvements from the 1.0 version that we'll be going through. The first thing to mention just up front is that I find it really handy to turn on in the Asset Manager under the Configuration tab, the Asset bar, so setting it to display a menu of all definitions. So by default, this is off, but if you turn it on, then you can very easily see which version of nodes you're using. So you can identify if you're working with Voronoi Fracture 2.0 or 1.0 and so on. So one thing to mention up front that's a little bit harder to directly demo is that one goal with the new version was to modernize the internals quite a bit. So the inside of Voronoi Fracture has been redone quite a bit, and it's also been made compilable. So now you can use Voronoi Fracture in your compile blocks, and we've also made a number of other HDAs like connect adjacent pieces and so on compilable, so a lot more of the destruction tools can be wrapped up in compile blocks for efficiency. So there have been a number of changes with Voronoi 2.0 to the parameter interface that we'll get into shortly. Generally, though, these changes are either for simplifying some common workflows. We'll see a few useful options for recursive fracturing, and also removing some deprecated options that weren't really a good idea anymore. Things like the options to create a separate primitive group for every single piece, which is a lot less efficient than the standard modern approach of creating a name attribute to describe the pieces. One very notable change you'll notice is that some of the options for clustering and interior detail that were present on the old version of Voronoi Fracture aren't there in the 2.0 version. And they've been moved into separate SOPs now. So there's the RBD Interior Detail SOP and the RBD Cluster SOP, which you can see in the tab menu. We'll get to those shortly, but the idea with this change was to make the fracturing process more modular. So for example, the interior detail can be applied later on in the SOP chain after you've already cached out the results of your fracturing, and then you can separately handle your low resolution and high resolution pieces. And you can also use it with other fracturing methods like Boolean, which we'll talk about later on. And the same goes for RBD clusters. So now the clustering process is done post-fracturing so that you're not necessarily having to refracture your geometry because the clustering settings have changed. So we'll take a look at those settings afterward, those new nodes afterwards, after we've gone through the new settings in Voronoi 2.0. So right here, I've got the two versions side by side, the 1.0 and 2.0 versions. And probably the first thing you'll notice is that the number of inputs and outputs are different. So the first two inputs are exactly the same as before. So you input the geometry that you're going to fracture. And then the second input is all of the cell points for the Voronoi cells. So just like before, you can create a volume, scatter some points in it or something like that to generate the points that are going to define the centers of the Voronoi cells. So we get the same fracturing results with 1.0 and 2.0. The third input, though, has disappeared. So in the old version of Voronoi Fracture, this let you provide a custom depth volume, which was just used for the interior detail settings. And so because that's now in the RBD Interior Detail SOP, that option isn't on Voronoi Fracture. And then the output, of course, is the same as before. You just get your fractured geometry, but you'll see in Voronoi 2.0, we also have this second output here. And what this lets us get is a constraint network that gives us the connections between all of the adjacent fractured pieces that were produced. So this was actually something you could sort of do in the old Voronoi version. That SOP was built before SOPs were able to have multiple outputs. But if you object merged this constraint network geometry from inside of Voronoi Fracture, you could get some form of constraints from it. The downside with this old approach was that it was just basically doing a tetrahedralized SOP between all of the centers of the pieces. And so if you had concave geometry, it didn't really give you the kind of results that you would expect. So that method has been improved quite a bit in the new version. And so you're just going to get connections between the directly adjacent pieces that were created by the fracturing process. And it's also done very efficiently by using some information from the fracturing process itself. So it's not just doing sort of the blind connect adjacent pieces approach of scattering a bunch of points on the geometry to find the connections. So it's a very efficient way to get either a starting point for your constraint geometry or just some handy information about which pieces are adjacent to each other. So if we wanted to use these constraints in a sim, all we would have to do is set up the usual constraint network attributes like the constraint name and constraint type primitive attributes. Out of the box, it already has a rest length attribute that's been computed for us, and it also has the name attribute and point position for the pieces that it's attached to. So now let's take a look at some of the options, the new version of Voronoi Fracture. So in the Pieces tab, we've got a bunch of options for how the pieces are named and some stuff for how their geometry is set up. So just like before, there's the Create Interior Surfaces option, which lets you control whether the inside faces are created during the fracturing process. So we'll see if we turn that off. We'll just get a hollow shell. So this is a good option if you're trying to fracture 2D geometry or if you want to produce a hollow shell from the fracturing process. There are a few options that were removed from Voronoi 1.0, like the option to fuse the input points, disconnect the inside surface from the outside surface, and so on, because these weren't typically used very often, and they can very easily be done with a separate SOP, like a fuse SOP or a primitive split SOP before or after the fracturing process. So the interface has been streamlined a little bit there. One thing you'll notice is that the Visualize Pieces option isn't available anymore. Instead, you have this Visualizer action button, which we've seen before on the Convex Decomposition SOP, and it also appears on a few other SOPs like the Attribute Noise SOP. And so what this will do is it'll add a visualizer for the name attribute. And so you can just turn that on, and instead of having to recook your SOP and potentially invalidate downstream geometry by adding a color attribute, instead just turn on a visualizer and it doesn't force the node to recook and potentially redo some heavy fracturing processes. So by default, this is what you should probably be using to visualize your points. But if you want to, you always have the option of just dropping down a color SOP, setting it to primitive and random from attribute to generate random colors based on the name attribute afterwards. With the name attribute, actually, one other useful new option is by default, of course, it will just set the name attribute to be piece 0, piece 1, and so on. But you also have the option to append to the existing name attribute if there was one. So in this example here, just at the top, I've added an optional switch that I'll turn on. So I've already done one level of fracturing. And then if I send that fracture geometry into another Voronoi fracture, I have the option to append to the name attribute instead of just blindly overwriting it. So in this case, my input geometry already had a few pieces like piece 0, piece 1, and so on. And then by default, if I were to feed this into Voronoi again, it would just overwrite the name. So now I have piece 0 to piece 308. But instead, I have now an option to make it easy to just append to the name attribute. So I could do a dash, for example, as my name prefix, and then I get names like piece 1-308 and so on. And so this makes it a lot easier to track the hierarchy if you're doing multiple levels of fracturing. There also have been a couple changes with the normals options. So it's now a little bit more explicit about what's going to happen. So by default, computing interior vertex normals is turned on. And then for the exterior normals, there's a few options for what happens. So by default, it will preserve any existing normals. So if you already have vertex normals on your geometry, for example, it won't recompute them. But if you don't have any normals on your geometry, it'll add normals using this cusp angle. So in this case, we've got vertex normals that have been added to our geometry, even though the input, or actually in this case, the input did have normals because I had pre-fractured it, but my original input didn't. And then you also still have the option to recompute the normals if you want to overwrite any existing normals that were being fed in or turn off normals entirely. So the options are a little bit more explicit than before in terms of what will happen if you have some pre-existing normals on your geometry. Then in the output attribute section, there are a couple new options. So one is this attribute name prefix. And what this will do is for any of the attributes and groups that are being created here, it'll let you easily add custom prefix to any of those options. So in this case, I've added a prefix of custom to my inside and outside groups. So now I can easily get unique names for all of these groups if I want to do multiple levels of fracturing and then get separate groups from each of them. Just like before, you can turn on an attribute to get an integer ID with the piece number, which is this piece attribute here, as well as an attribute with the point ID of the original cell point that produced this piece. And then there's one change here. In the old version of Voronoi Fracture, you could get an attribute for the primitive clip point. And this would basically be for any of the interior faces, which of the cell points it was clipped against in order to produce that face. This has been changed a little bit, so now it's the primitive clip piece. So instead of being this Voronoi cell point from the piece on the other side, it's actually the piece number. So this ends up being kind of important if you have concave shapes and things like that, where one Voronoi cell point can actually produce multiple different pieces. So this is a little bit more precise and more reliable to work with now. Just like before, there's still the options to generate the interior and exterior groups for the fractured pieces. So we can see that in the spreadsheet here, if we're looking at the exploded view. Let me just delete the asterisk there. So now we can see our inside and outside groups just like before. And there's one option to make the behavior a little bit more explicit with what's going to happen if you're doing multiple levels of fracturing, which is this merge with existing groups option. So the default behavior here is that if the input geometry already has an inside and outside group, any of the new primitives that are created from the inside surfaces will be added into the existing outside group, but not overwriting it. And then the outside group will be just left as is. So if you do a sequence of fractures, you'll just end up having an outside group that contains the original outside primitives, and then your inside group accumulates all of the inside primitives that were created from all of the fractures. So this is the default behavior, but if you want to turn that off, then it'll behave as though those groups didn't really even exist on the input geometry. So the outside group will have all of the input primitives, and the inside group will have all of the new primitives that were generated by the fracturing process. Then just like before, you have an option if you want to copy any point attributes from the original cell points onto the points or primitives of the fractured pieces. And then there's also a new option now that we have this option to output to the constraints, is that you can also transfer attributes onto the constraint network geometry. And then finally at the bottom, there are just a few advanced options for the fracturing process, which are basically the same as what you had on the original Voronoi fracture. So either auto-detecting or using existing triangulation for Voronoi split. The auto-detect option is usually what you want. And then a couple options for how to maintain piece numbering if you wanted to maintain some correspondence with the point numbers on the original cell points, and then an offset parameter for the cutting plane. All right, let's take a look now at the RBD interior detail SOP. So one of the first things that you'll notice is that this has 3 outputs, which is a little bit different than what we were just seeing with Voronoi Fracture. So just like before, the geometry output and the constraint geometry output are outputs 1 and 2. Then the third output provides proxy geometry. And so this lets you carry along a low-res or proxy geometry representation of the geometry alongside the fracture geometry and also alongside the constraints. This is kind of a similar workflow to what development tools are doing, if you've already used that in Houdini 17, but instead of the third output being the collision geometry for vellum, it's being used for the proxy geometry for the RBD nodes. So in the case of RBD interior detail, the main operation of adding detail to the interior faces is just applied to the first geometry, so the high-res geometry in this case. So we're just taking the original geometry from Voronoi Fracture, and then RBD interior detail is going through the first input's geometry and adding some more resolution and noise to the interior faces there. The constraint output is just left as is, so it's just acting as a pass-through in this case. So the constraints are just unchanged because adding interior detail doesn't affect any of the constraints. And then the proxy geometry input is a little bit more interesting. So if I had already had some proxy geometry and I passed that into the third input, it'll just be directly passed through to the output. So it'll just be left as is. The interior detail is just being applied to the high-res geometry. But if I didn't actually provide any proxy geometry, the SOP will take the original input geometry and provide it as in the third output as my new proxy geometry. So this immediately gives you a separate split in your network for the high-res and low-res geometry if you need to do separate things with them. So let's take a quick look now at how the SOP works. So since it's now a separate SOP and it's not part of Voronoi Fracture anymore, you do need to specify what polygons or what primitives you want to apply the interior detail to. And so this is where the interior group parameter comes in here. So it defaults to inside, which matches the name of the groups that Voronoi Fracture creates by default. So we'll just take a quick look at those in the network editor here. I'll just disable the interior detail and go back to the exploded view and go into the group picker. So Voronoi Fracture by default will create a group called outside, which has the original faces before fracturing happened, and then an inside group, which has all of the new interior faces that got added as part of the fracturing process. And so if you've left these parameters as default, then RBD interior detail, because it uses inside by default, it'll just work as is. But if you have changed around or disabled these groups on Voronoi Fracture, you might need to take that into account when you're setting up the interior detail and provide your own group there. And then next up in the geometry tab, there's a few options for what you want to do with the polygons themselves. So you have an option for whether you want to add any detail to those polygons by doing a bricker operation. So if you turn this off, the geometry is just left as is, which in this case isn't a high enough resolution to do anything interesting. But if you already knew that your polygons that you were trying to apply the detail to had already been divided enough, then you could turn that off. And then otherwise you can control how finely or coarsely you want those polygons to be divided. And then next up, you have an option to recompute the interior normals, or you can just leave them as is. And then there's also an option where you had any quads or non-triangular polygons in your output, you can triangulate them if they ended up being non-planar after applying the displacement. So then in the next tab, you've got a whole bunch of settings for the noise that's going to be applied. And this basically mirrors a lot of the parameters you're probably familiar to from the unified noise VOP and the mountain SOP and so on. So the main control here is the noise amplitude, which is the amount of displacement that's being applied. And then on top of that, you've got all of the usual noise controls to switch between different noise types, change the frequency of the noise, offset, and so on, and then some of the more advanced noise controls as well. So you can use all of that to adjust the shape and style of the noise. And then at the bottom, you have all of the interesting controls for how the noise is applied to the interior faces. So first, we'll turn on the Visualize Noise Scale option, which gives us a nice visualization of how much displacement is being applied to each point. So by default, what the SOP will do is compute an SDF or sign distance field from the input geometry and use that for sampling the depth of each of these interior points so that it can then scale the amount of displacement so that you don't have points that are, right near the surface being displaced outside and things like that. And also to make sure you get a smooth transition from the outside faces to the noisy interior. So by default, it'll build that sign distance field using this resolution. But if you want to supply your own volume, you can also do that using the fourth output. So this is just like on Voronoi 1.0, there was that extra third input for providing your own depth volume. And so now it's on RBD interior detail as this extra input. So you could, for example, use an ISO offset SOP, build it from maybe the original unfractured geometry, switch this over to SDF volume, and then adjust your resolution and some of the more advanced construction parameters, and then pass that in as the fourth input here. And then that will disable the normal depth volume that's being computed by default, and it'll be used instead for the depth sampling. And I'm going to just disconnect that. Okay. So then next up, there's an option to clamp the amount of displacement based on the depth of the point from the surface. And the effect of this is a bit easier to see if I crank the noise amplitude up really high. So I'll just turn this up to kind of a ridiculous amount that looks pretty silly in this case, but it makes it a little easier to see what's happening. So if I turn this option off, you'll see that points that are near the surface, because the noise amplitude is so high, they can end up being pushed outside. And if I turn off the exploded view, you'll see that it's kind of messed up the silhouette of our geometry. So what this will do is clamp the amount of displacement to be some percentage of the depth from the surface so that it can't go outside. So if it's set to 1, then it's clamping it just enough to not be pushed outside. But if you have a really low resolution depth volume or something like that, that might not be perfect. So by default, it's just clamped to 90%. And then as you drag this down, the points can't be displaced as much. And at 0, nothing really interesting is happening. And then I'll just change my noise amplitude back to something that looks a little nicer. And then the bottom controls let you control how the depth from the surface is mapped onto the noise amplitude. So the default is using a bias curve. And so if this is set to 0.5, you end up getting basically just a linear interpolation. So the points that are right at the surface end up getting a noise amplitude of 0. And then the points that are at the deepest amount, that are the deepest from the surface, are going to get the maximum noise amplitude here. And then in between, it's just a linear interpolation. So then as you drag this value to either side, you'll get a curve that's biased in either direction. And then as an alternative to that, you can also use the depth of noise ramp, and this lets you just provide your own custom ramp so you can control the shape of this curve in any way that you want. So with these parameters, you can get a bit more control over how the points that are kind of near the surface get displaced to avoid having any artifacts that are being introduced by having a lot of noise being added to the interior surfaces. Next, we'll look at the RBD cluster SOP, which is used for clustering together fractured pieces into larger chunks. The workflow is a bit different than the clustering options in the old Voronoi SOP, partly because it's now clearly separated into a post-fracture step, but it's also been made into a tool that's more useful in other situations. So you can now use it for clustering together fractured pieces from other fracturing methods like Boolean, and you also have some more control over how exactly you want to create those clusters, whether it's by actually merging together pieces or by just setting up constraints differently to create the look of clusters. So let's start by looking at the old Voronoi SOP just for a refresher. So in Voronoi, if you turned on the cluster pieces option, then that would cluster the pieces into a few larger chunks, which we can see a bit more easily with the exploded view as well. And so that was controlled by the add cluster noise option, which gives you some control over the size, offset, jitter of the cluster noise. And then you also have some options for randomly detaching pieces or setting up constraint network that you would have to object merge out. But if you wanted to do some more custom clustering, the way that you would do that is by setting up a cluster attribute on the input points, so the input cell points for Voronoi Fracture. So in this case, if I had just used this wrangle here, all it does is divide the points into 2 different clusters based on their position along X. And so if I send that into Voronoi Fracture now and turn off the default cluster noise, we'll see that we end up just getting 2 clusters that are split along the X-axis. And then as I change this around, see my custom clustering taking effect. So the one downside with this approach was that it was kind of intertwined into the fracturing process, right? So if I wanted to set up my own cluster attribute on the points, I'm having to do that by adjusting the input points of Voronoi Fracture, which means that that's also causing the fracture to happen again. So you'll notice that it's kind of laggy as I'm trying to change around my clustering settings because it's actually modifying the inputs to Voronoi Fracture and forcing me to redo some of the fracturing work. So that's not really ideal. So let's take a look now at RBD cluster over here. So you'll see that it's a 3 input, 3 output node, sort of like what we saw with RBD interior detail. So we have the geometry, the constraints, and the proxy geometry. And it still allows you to do a similar point-based clustering approach as before, but now instead of doing it on the cell points for Voronoi Fracture, you can just do it on the constraint networks points. So we'll take a look at that here. So over here, I've got my constraint geometry. And then if I do the same sort of clustering along the x-axis approach as before, and then send that into RBD cluster, well, it can turn on the visualizer for the clusters, and we'll see that we're getting split into 2 separate chunks as before. So the nice thing with this approach is that it's done after the fracturing process. So you could cache out the results of your fracturing and do this clustering at any point later on. And that also makes it very easy to iterate on because now it's super fast. All you have to do is just change around the name attribute. And so if I change around my clustering settings, it just updates in real time and I can test this out very easily. So let's take a look at the parameter interface. So we have kind of similar looking options as before, but now it's a little bit more explicit about how the cluster noise settings that are provided by default are combined with the cluster attributes that you might have set up on your input geometry. So first, you can specify what attribute you want to use for the clustering. It defaults to just cluster. And then you have the same offset, jitter, and size parameters that we had on the old Voronoi Fracture SOP. But then here we have an option to be explicit about how we want to deal with the incoming cluster attribute. So you can preserve existing clusters, which will let you just override or will ignore all of the default clustering parameters if you have a cluster attribute already set up on your geometry. And then otherwise, you also have options to overwrite or not do anything. And then on top of that, there's also the random detach option, which will randomly split out some pieces from their cluster and just leave them as isolated pieces on their own. And the way that this works is just by setting the cluster value to -1. So cluster values that are less than 0 are interpreted as being just pieces that should be left on their own. So we can see that here if let's just add something into our wrangle. So if 0.0, let's say we want to leave on its own, we can just set its cluster value to -1. And then if we probably need to turn to an exploded view, yeah, we'll see we have one piece that's been left on its own and hasn't been added into any clusters. So with this, you can get a bit more control over how exactly you want the clustering to happen very easily, and also how your own detachment can be implemented. But you can also just use the random detach option and control the ratio of how many detached pieces you want, and also adjust their random seed. And then there are a couple different modes for how you want to actually apply the clustering and have it take effect. So the default that we've been using here is the combine pieces mode. And so the way that this works is it just does the clustering by adjusting the name attribute, so merging together pieces into one single larger piece. And so this is a little bit similar in concept to how the proxy geometry stuff we looked at earlier with sphere packing and convex decomposition worked. So in this case, we started out with 502 pieces, and then we now just have 70 pieces. I'll turn off the random detach maybe to make it even easier to look at. So now we just have 5 pieces. And if we look at the spreadsheet, we went from having names like piece 0, piece 1 up to piece 500. And now we just have pieces named cluster 0, cluster 1, and so on according to this name prefix we have here. So all that it's done is just set up a new set of names to combine some pieces together into larger clusters. And so just like we were doing with the proxy geometry before, in DOPS, you could just turn on the compound shape option and have a compound shape be built up out of all of the original Voronoi pieces in that chunk. So you can very efficiently set up collision shapes for these concave clustered pieces. And so this approach is really good if you have pieces that you never want to break apart. So if there aren't going to be any constraints between these objects, they're just going to be combined together into one object for the simulation. So it's a very efficient way of setting up compound shapes, but it has the downside that you can't easily break apart any of these chunks unless you go down the dynamic fracturing approach or something like that. So the other mode that you have is group constraints. And so this works actually in kind of a similar way as the old glue cluster SOP, which was made for operating on glue constraint networks, but it's been made a little bit more generic so that you can use it with other constraint types and kind of do your own thing with it. So the idea here is that in this mode, it won't actually rename your pieces. You'll still have the same number of input pieces as before. So we'll see we have 500 pieces, and we still have our usual names of piece 0, piece 1, and so on. But instead, it just adjusts our constraint network and creates some primitive groups. So we'll take a look at that here. I'm just going to turn on the random detach option as well so that we have a few detached pieces to show the effect of that. And so it creates 4 different primitive groups. So one for intra-cluster, cluster to cluster, cluster to piece, and piece to piece. And it's a little easier to look at that if we turn off the visualization and go into the group visualizer. So we have these 4 groups. So one is going to be cluster to cluster, which is the constraints from pieces in one cluster to pieces that are in a different cluster. And then you also have the intra-cluster, which are all of the constraints that are inside of one cluster of pieces. And so this lets you do things like setting up, say, stronger glue within a cluster and then weaker glue in between clusters. And so that'll give you the effect of having a chunk that can then break apart and then even break apart further if there's really strong impacts. So this is useful for kind of shaping the clusters and letting them dynamically break apart during a simulation. And then on top of that, if you are doing the detachment option or you did your own custom clustering and not every piece was added into a cluster, you'll also have the groups for constraints that are in between separate individual pieces, and then also the constraints from pieces that belong to a cluster to pieces that are not part of any clusters. So you end up with these 4 different primitive groups, and then it's up to you to do whatever you want with them afterwards. So you could set up different constraint properties and things like that. So with this approach, it won't be as fast as doing the combine pieces approach because you aren't actually changing the number of pieces in your simulation, right? In this case, we still have 500 pieces, so it's not as efficient as combining everything into, say, 5 giant clustered pieces, but it gives you the flexibility of being able to set up your own constraints and do kind of custom stuff to let these chunks break apart further on. So it's a more flexible approach if you want to do stuff with clusters that are going to be breaking apart and not necessarily staying together as one solid object for the entire simulation. So related to what we were just looking at with RBD cluster, where we had the option of setting up different primitive groups on our constraints, another new SOP that we've added is the RBD constraint properties SOP. And so the idea with this SOP is it's just a simple higher level tool for setting up the common constraint properties and primitive attributes for constraint networks that Bullet expects. So this is just a nice way to avoid having lots of wrangles and attribute creates for setting up the usual Bullet attributes. So with this SOP, you can first specify your constraint groups, so the primitive groups within your constraint network. So here we could use our cluster-to-cluster groups, for example, that we had set up from RBD cluster, and just set up the constraint properties for those constraints, which we can see with the guide geometry here. And so then you have a bunch of parameters for setting up the constraint properties. You can pick between different constraint types. Currently, it's glue and soft constraints, but this will be expanded in the future for more constraint types. And then set up the constraint name. So this matches the name of the constraint in DOPS. So you can change this if you're setting up multiple instances of the glue constraint relationship node in DOPS. But by default, it just matches the name of glue or soft. And then you have all of the usual parameters that you'd expect for glue constraints like strength, half-life, and propagation rate, and so on. And there's also a built-in option to add a bit of variance to the strength. So if you look at the constraint geometry, we'll see that it's just added all of the standard primitive attributes that we're used to just for the primitives that are in the group that we are operating on. So we have the constraint name attribute here. The constraint type attribute is just left out for glue because it doesn't actually matter. Glue constraint just creates compound shapes, so it doesn't matter whether you're affecting position or rotation. And then we have the impulse, half-life, and all of the usual attributes that you might set up for the glue constraint. So these all default to 1, so they'll act as multipliers for the values that you have in DOPS. But if in DOPS you're just kind of leaving them as 1, then you can set these to the true values and do all of your setup in SOPs. And then for soft constraints, in addition to the stiffness damping ratio and all of its standard parameters, there's also the degrees of freedom option, which defaults to position and rotation. So this corresponds to setting constraint type to all, and then setting it to position only or rotation only corresponds to setting constraint type to position and rotation. So this is just kind of a nice way of quickly setting up the constraint properties without a lot of custom wrangles and things like that. And then for glue constraints, the SOP also exposes the next constraint option. So I'll just turn that on, which is this switch constraint type when broken. And so with this, it sets up these two attributes, next constraint name and next constraint type, which are attributes that the bullet solver itself will recognize. So if the bullet solver decides to break a constraint, which in the case of glue constraints is going to happen if the impact value gets to be larger than the strength threshold, the solver will then immediately switch over the constraint type and constraint name attributes over to these new values. So it'll give you an immediate transition from glue constraints into soft constraints or whatever other constraint type you were using. So this can just be a handy way of avoiding having to write SOP solvers in kind of common scenarios where you just want to immediately switch to some other constraint type when the glue constraint gets broken. So then in RBD constraint properties, you can then also set up the stiffness and damping ratio parameters and so on for the soft constraint that you're going to be switching into. So to wrap up our section on the lower level fracturing tools, we'll take a look at the Boolean Fracture SOP, which is another new SOP in Houdini 17. So the Boolean Fracture SOP is kind of just the Boolean equivalent of Voronoi Fracture, but based around Boolean instead of Voronoi Split. So if you look at the inside of Voronoi Fracture, it's really based around the Voronoi Split SOP that handles the actual cutting of the geometry. And then the rest of Voronoi Fracture is just based around making it convenient to use Voronoi Split. So things like computing the name attribute, recomputing normals, transferring attributes from the input points, setting up the standard groups and attributes that give you some information about what happened during the fracture, and so on. And Boolean Fracture is very similar, except it's based around a Boolean shatter operation. And then still, as with Voronoi, it handles all of the standard things like overwriting or appending to the name attribute and setting up normals and so on. And so this makes it a lot more convenient to do Boolean-based fracturing, both by eliminating a lot of the busy work, but also making sure that it's consistent with the output you would get from Voronoi. So you still have the name attribute, vertex normals being computed, inside and outside groups, and so on. So it's a bit easier to have higher level fracturing tools as well that can use either Boolean or Voronoi and still produce consistent attributes on the output. So in this example here, we'll just take a look at what I did. So this is just the standard pig geometry, and then I've scattered a few points inside its volume, given them random orientations with attrib randomize, and then instanced a few grids onto them, and then added some interesting noise to them with the mountain SOP. So with Boolean Fracture, the second input is different from Voronoi. So instead of being the cell points for doing a Voronoi split, it's going to be the input cutting planes for doing a shatter operation with the Boolean SOP. So then if I feed those cutting planes in, we'll see that it's sliced up our geometry into some nice and interesting looking shapes. And then as with Voronoi, the outputs are exactly the same. So the first output, of course, is the fracture geometry. And then the second output is the constraints between all of the adjacent pieces that were produced by the Boolean SOP. So just like with Voronoi, this constraint network can be really handy for either using as the starting point for your constraint network in the sim, or just for getting some interesting information about which pieces ended up being adjacent to each other after the fracturing process. And then the parameter interface for Boolean should look pretty familiar after looking at Voronoi. So just like with Voronoi, we have the usual option for setting up the name attribute along with a visualizer that we can turn on to visualize pieces. And then we can also append to the name attribute instead of overwriting to it if we're doing a recursive fracturing process. The interior and exterior normal settings are exactly the same as Voronoi, so we can turn on or off computing interior normals as well as preserving or recomputing the incoming vertex normals. And then the output attribute section is also fairly similar, but there's a few differences between the different fracturing methods. So just like with Voronoi, we can use the attrib name prefix if we want to add our own prefix to the inside and outside groups and any other attributes that we're creating. And then we can also turn on the option to set up a primitive piece attribute, which has just an integer ID for the pieces that were created. Unlike Voronoi, there are a couple fewer options because we don't have the input cell points. So there's no option to, of course, set up an attribute for the cell point that produced that piece because we don't have the same concept with the cutting surfaces for Boolean. And Boolean already handles some attribute transfer for transferring attributes from the interior surfaces onto those pieces. And then just like with Voronoi, we can still set up the interior and exterior groups, which default to inside and outside. And we have the same option for whether we want to accumulate those interior and exterior groups over multiple fracture operations, or if we want to just overwrite them. And so then finally at the bottom, there's also a few Boolean specific settings that are just promoted up from the Boolean SOP. So you have the detriangulation settings, and then a few of the more advanced options for the Boolean operation. So you can just refer to the Boolean SOP's help for any of those if you find yourself needing to tweak them. So on top of all of these core fracturing tools that we just looked at, we've also added a new node, RBD Material Fracture, that provides some higher level material-based fracturing options. So the idea here is to provide some very artist-friendly tools to fracture common things like glass, concrete, and wood, and handle a lot of the tedious tasks like setting up constraints and proxy geometry, but still provide enough control to be able to art direct the look at the fracture. So let's take a look at this now. So I'll drop down the RBD Material Fracture SOP, and let's take a look at some of the top-level parameters. So at the top here, we've got the standard group parameter, which is still worth mentioning because there are a lot of interesting things we can do with this, as we'll see later on. So you can use the 3 inputs and 3 outputs to chain together multiple RBD material fracture SOPs, and then use the group field to isolate different parts of the geometry to fracture. And we'll see that as we go ahead to doing a full example later on. Next up is the material type, which lets you switch between concrete, glass panels, and wood. And then the fracture namespace option lets you easily add an extra prefix to all of the fractured pieces that are created by this node, so that you can identify them easily later on. So we'll see that the default names here, for example, are concrete 00, concrete 01, and so on for each of the pieces. But if I turn this on, then we'll get this extra name being added into the beginning of all of the piece names so that we can identify those later on if we need to. The fracture per piece option we'll take a look at later on. It's a little bit more interesting to talk about once we've actually seen the parameters of the different fracturing methods. And then each of the different fracturing methods has its own guide geometry options, but there are a few standard ones that all of them have, so I'll just go through that now. So the default is to not show any guide geometry. But then you can also turn on the fracture geometry guide, which will just highlight the pieces that were produced by this node. And so this is mainly useful when you're also using the group field, and it just gives you a quick visualization of what the SOP itself was operating on. And then there's also the constraint network visualization, which lets you see the constraint geometry from the second output. There are also a couple interesting visualization options we'll see here once we're doing multiple levels of fracturing on pieces, because then we can see the constraints that were just being added or changed around by the particular fracturing operation when we're just operating on a particular group of pieces. So first up, we'll look at the concrete fracturing. And so this is really a primarily Voronoi-based approach, so the workflow should seem pretty familiar, but it adds in a lot of nice options for getting interesting size variations, doing sub-fracturing or chipping off the corners of certain pieces, getting edge noise and so on, so that you have less Voronoi-looking pieces being produced. So let's start by turning on a single level of fracturing, and I'll also turn on the primary volume visualization here. So the idea here is pretty similar to what you would get from the standard shatter shelf tool, where you're taking the input geometry, building a fog volume from it, and then scattering some points in that volume to use as the seed points for Voronoi Fracture. So down here at the fog volume section, we have the volume resolution for the volume that we're producing, but then there's also some noise controls here. And so this is just adding noise into the density values of the volume. So if I set this to 0, for example, we just have a uniform density volume. And if I increase the number of scattered points, we'll see that we basically just get our points being scattered uniformly throughout the volume, and we just have a bunch of evenly sized Voronoi chunks. And then if we start adding some interesting settings to this noise, we'll see that the scattered points are getting concentrated in certain areas of the volume. And so now we've got some more interesting shaped fractured pieces being produced. So we can use the noise frequency option to control the shape of the noise, and then we can also use the noise offset to move that pattern around. And then there's also a cutoff option if you want to cut off any low density areas of the volume to avoid having any points scattered there. So then in the cell point section, we can control how many points you want to be scattered, which roughly will correspond to the number of pieces being produced. And then we can also change around the seed that's being used for the random scattering. There's also a useful option to be able to provide your own input points. And so that uses this extra fourth input for driving the results of the fracture. So I'll just do a really quick example of that. So I'm going to create a box and just position this up near the corner, let's say. And then I'll use an ISO offset to just create a fog volume. And then we'll scatter a few points in here. And maybe drop that down to 100. And then we'll wire these points into the fourth input. I'm just going to scale this down a little bit so that they're a little more concentrated. And so then if I turn on the use input points toggle, we'll see that those are being added into the points that were being generated from the volume. And so you can control a bit more exactly where fracturing is going to occur. So then one thing to mention when you're using the input points is that you can then also specify a group field if you want to only use certain points from the fourth input for this particular stage here. Then the other mode that you have to work with instead of scattering from volume is to scatter based on an attribute. And so in this case, I'm just going to turn off the volume visualization. It errors out right away because the attribute that it was looking for on the points named density by default doesn't exist. So one way of creating that is with the RBD paint tool, which is a handy new tool that we added. So I'm going to drop this down and switch over to that and make sure I have the soft fall-off visualization on, which I do. And so this lets you paint attributes easily on your fracture geometry. And it defaults to creating a density attribute, which matches what RBD Material Fracture was adding. So one thing to mention here is that my input geometry is very low resolution. So I can use the option on here to divide the geometry so I have some more points to paint on. And then I'll just turn on my visualizer again and paint in kind of these areas here. And then if I switch back to RBD Material Fracture, we'll see that the pieces are being scattered in these high density regions. So we can control a little bit more precisely where exactly the fracturing happens. So this is very useful for kind of art directing the look of the fracture. And so you can switch between the volume-based or attribute-based scattering approach depending on what you need. I'm just going to switch back to the default settings and maybe reduce this down to about 20 points, and I'll turn off the paint operation as well. So now that we've done sort of our first level of fracturing, we have the option to do an arbitrary number of levels of fracturing. So we can continue sub-fracturing some of these pieces that were being produced. So I'll add on an extra level of fracturing here. And then now this fracture ratio parameter that I kind of skipped over before becomes a lot more important. Just to see the results of this a little more easily, I'm going to turn off the noise frequency so we just get uniformly scattered pieces, and then maybe scatter, say, 50 points in each of them. So then the fracture ratio controls how many of the pieces from the first level of fracturing are going to be sub-fractured again. So if it's set to 1, then everything gets sub-fractured. And then as I change this around, maybe only certain pieces get selected for sub-fracturing. So this lets you keep some larger chunks around, while subdividing some of the other pieces to get some smaller chunks in your result. So then the fracture ratio is just controlling which percentage of the pieces get selected for sub-fracturing. And then the fracture seed just lets you control that random selection. And then just like before, you have the same controls over scattering, so you can scatter from volume or from attribute differently at each step, and also use certain input points if you want to control the results of the second fracturing level differently. And one thing to mention is that you might want to turn down the volume resolution for the additional levels of fracturing it tends to not be as important once you've got a lot of smaller pieces that are each being individually subfractured. So you often don't need to have as high a volume resolution, so turning this down to something like maybe 40 or 30 will probably still give you very good results. Then on top of that, there's also an option to turn on chipping, which basically just acts as an additional level of fracturing on top of the primary fracture. And so all that this does is it just chips off the corners of certain pieces given the overall ratio parameter and then also a seed. So it's just acting like an additional level of fracturing if you want to have a bit of chipping near the corners of certain pieces. And then on the detail tab, we have a few options to control the edge detail and interior detail. So I'll switch back to the exploded view so we can see what's going on. And if I turn on the interior detail, we'll see that it's kind of similar to the RBD interior detail SOP. And actually, there is just an RBD interior detail SOP inside of RBD Material Fracture. So the interior faces are going to be divided according to the detail size. So this controls how detailed or how small the details are on the interior surfaces. And then we have a noise amplitude for controlling how much displacement we have on the interior faces, and then a few noise parameters that are promoted up. And then there's also a depth volume voxel size we can control as well. The other option that's a bit more interesting is the edge detail option. I'll just temporarily turn off the interior detail. So the edge detail option will switch over to a Boolean-based approach for cutting the geometry, and it adds some interesting noise along the edges. So you get some, instead of getting the straight fracture lines from Voronoi Fracture, you get some interesting curvature along the lines and a bit more noise. So the noise height parameter controls how much noise is being added to the edges. So in this case, maybe 0.2 or something like that looks okay. And then the noise element size just controls the shape of the noise and how high frequency or low frequency it is. Along with that, because it's a Boolean-based operation, and the detriangulate options have also been promoted up, so you can control whether you want to do detriangulation or not. And then, as before, the detail size controls how high resolution the edge noise is. If we go back to the exploded view, you'll see that we do get a bit of interior detail as a result of the cutting planes from the edge noise, which you can also turn on with the guide geometry option. But you still have the option of using the normal interior detail as well if you want to have a bit more control over the interior noise separately of the noise that's being added along the edges. So next up, we'll take a look at the glass fracturing. And the glass fracturing is primarily driven by impact points. So these will be the points where the cracks originate from. So the default behavior here is to just scatter a number of points. So in this case, it defaults to 1, but I can scatter multiple points and change around the random seed to get different behavior and so on. But similar to the concrete fracturing, we also have the option to provide our own impact points using the fourth input. So in this case, I could, just for a simple example, scatter a few points on the input geometry like this, and then feed those into the fourth input here, and then either turn off the original scattering or combine both together, and I can use my custom impact points and change those around if I want to have a bit more control over the fracturing look myself. So I'll just go back to the default settings for now and turn off use input points and go back to scattering my own points. And then to start out, I'll turn off a few of the advanced options so that we can turn things on one by one and see the effect of each of these settings. So I'll turn off the edge noise and also crank up the width for the concentric cracks to turn them off for now. And I'll just, I think, revert to having one impact point for now, just so it's a little easier to see. So the first thing here is creating the radial cracks, which are just emanating in each direction from the source impact point. So this is controlled by the radial crack number. So this is how many radial cracks you're going to get. And then you also have some variance controls that if you have, let's say, multiple impact points, you can have a bit more variance in terms of, each of them not having the exact same number of radial cracks. So you have a variance and seed control for that. I'll just go back to having 1 point. And then on top of that, it then performs another level of fracturing. So it takes all of the separate pieces that were produced by the radial cracks and then fractures them further to produce concentric cracks in a circular pattern. So I'm going to first turn off the noise settings here and then start bringing the minimum width of the concentric cracks down to a more reasonable level. So as this decreases, we'll see that we get a bunch of concentric cracks with this minimum width. And then there's also this impact spread, which controls how close or how far away from the impact point the fracturing occurs. So if we crank this up high, then the impact kind of spreads farther out and we get a lot more fracturing happening further away from the impact point. And then to make the pattern more interesting, instead of just getting a spiderweb pattern, we also have some noise settings for adding some discontinuity to these fractures. So if we turn on the concentric noise, we'll see that we can visualize this noise pattern. So the impact spread is scaling this noise pattern based on how far away we are from the original impact point. And then on top of that, we can add some noise settings for adding some more discontinuity and reducing the number of concentric cracks that we get into some more interesting looking shapes. So we'll see that it's basically acting in sort of a Voronoi based manner where we have cell points for each of these concentric cracks. And then if they're in an area of high noise, they're allowed to stay around, or in this red area, the cell points are allowed to stay there. And then if they're in areas that aren't very high density, then those points are going to be removed. So we can play around with the discontinuity settings to get sort of higher frequency or lower frequency noise and get a bit more control over the exact look of how these concentric cracks are spreading out from the origin. So then on top of that, we can also add chipping, sort of like what we saw in the concrete fracturing, where we can add some chipping to the corners of the pieces. We had the same overall ratio and overall seed parameters as before. And then there's also a parameter for how many corners basically will get chipped off per piece that gets selected for having chipping applied to it. And then on top of that, we also have some options to add some higher detail to our render geometry separately from our proxy geometry. So if we turn on edge noise, we'll get some interesting warping and noise happening for our high resolution geometry, but the low resolution geometry will still remain fairly coarse. So let's switch back to the edge noise. We have a couple controls for fading away the amount of distortion that's happening from the origin and from the border. So if we decrease this, we'll see that the noise pattern can end up kind of distorting the shape around the original impact point. So you have the option to kind of have a smooth fade away from the impact point so that you kind of maintain some of the original look. And then likewise, near the border, you can avoid having too much distortion being applied. So the default parameters are generally pretty good for this. So you get kind of an interesting shape on the interior of the glass, but without affecting the edges and also the impact points area. And then we have similar parameters to what you had on the concrete fracturing for the edge noise. So you have an amplitude for the amount of displacement in either direction, and then also some control over how high frequency or low frequency the noise that's being applied is. So for the proxy geometry, what the SOP tries to do is deform it a bit to match up with the geometry from that had the edge noise applied to it. So I'll just turn off the exploded view to kind of visualize that. So what it'll try to do is if there was a fair amount of displacement happening for these pieces, it'll try to deform the proxy geometry so that it kind of lines up with the distorted shape from the high resolution geometry. But that obviously can introduce some concavity if there's a lot of bending around the middle of a piece and so on. So you do have the option to turn on a convex decomposition, so you can enable that and then adjust the max concavity and possibly divide some of these proxy pieces into smaller sizes to get a more accurate proxy representation. So you can use that if you find yourself getting a lot of concave pieces being produced by the glass fracturing. And then as with the other fracturing methods, there's some built-in options if you want to set up the constraint properties for the constraints that are produced. So in this case, for glass fracturing, we've got a few different primitive groups that are being produced. So we have constraints for the pieces that were produced by the radial fracturing, constraints for the cuts that were made for the concentric fractures, and then also some constraints that were produced for the pieces generated by the chipping. And so you can, if you want sort of basic constraint setup here, you can just get some glue settings here. But then if you want to do more custom setup, and we'll see this later on, you can use RBD constraint properties afterwards and target some of these different primitive groups that were being created by the fracturing process. Next, we'll take a look at the wood fracturing. And so the wood fracturing is entirely Boolean based. So it's going to work based on setting up cutting planes to carve out the grains of the wood, as well as creating splinters and cuts in the other direction. So let's take a look at how that works. So under the guide geometry options, we have some options to visualize the grain, cut, and splinters. So we'll start by looking at grains and also turn off the cut for now so we can just see one piece at a time. So the idea with the grains is to make cuts along the longest direction of the wood to create the grain lines. And so by default, this will auto-compute the direction based on the bounding box. So the cutting planes are aligned along the longest axis. You can also provide your own direction vector if you want to. And then the grain spacing and offset just control where the cutting planes are spaced. So as this gets increased, we have more or fewer cutting planes, and they're also closer together. And then the grain offset controls how much randomness is applied to the position of each of the cutting planes. So as we increase this and also maybe change around the seed, you can have cutting planes that are less evenly spaced if you don't want as much of a regular look. And then on top of that, you can control the noise of the cutting planes. So we have the grain detail size, which is how much the cutting planes are remeshed. So as we increase this, they're very low resolution cutting planes, and so we get fairly low resolution pieces being produced. And then as we decrease this, we get some much higher resolution cuts being made. And then the height and noise size, I'll just switch back to the guide geometry. So this will control how noisy the cutting planes are. In this case, a smaller value probably looks pretty good. And so you can decide whether you want to have like perfectly straight grain lines or some slightly curved grain lines. And then the element size controls the shape of the noise. So I'll just revert these back to a kind of a good setting to continue on with. And so the next part is making cuts in the other direction of the grains to both fracture the wood and also create splinters. So let's switch over to the cut guide geometry and also turn that back on. So the default behavior here is to also auto-compute the direction for the cuts, and this will be in a perpendicular direction to the grain lines that we had created before. But again, you can also specify your own direction vector if you need to. And then just like we did for the grains, we can control the spacing and random offset between the planes, so we can have them be a little bit closer together, and then also change kind of what our random offset is, and also add some different seeds for changing around the look of that. And then similarly, we can also adjust the same sort of noise settings to control the curvature of these cutting planes, so the cuts that they're going to be making through the surface of the geometry. And then in this case, I kind of like the shape. So if we look at the exploded view, we can see we have something like that. And I'm actually going to turn back down these, or increase the spacing so that we have some fewer cutting planes, so we have some longer chunks to work with. The next part of this is adding splinters. And so this is done by adding an additional level of noise to the cutting plane so that it carves out some nice splinters from the geometry. And we can see that if we switch over to the splinters guide. And right now I had this turned off by default, so the splinter length was set to 0. Normally it's on by default so that you get some interesting looks. So as we increase the splinter length, we'll see that it's adding this very sharp noise in both directions to the cutting planes, so that it's carving out some splinter shapes for us. So we'll see something like that. And then as we also adjust the splinter density, so whether it's, our splinters are very closely packed together or are very wide apart, we can change around the shape of the splinters that are being produced. We can either have a very low density of splinters, which is not looking too good in this case, or if we crank up the density, we're getting some, sharper looking splinters being produced. And so then finally, the next option you have is clustering together the different pieces. And this is also on by default because it generally looks a little bit better for wood. So if you want to, you can also turn on clustering and then adjust the size parameters, which basically corresponds to what you would get from the RBD cluster SOP. It's just built in for convenience. So this will combine together some of the pieces that were produced by the splinters and cuts so that you get some more solid looking chunks of wood that still have some interesting detail for the splinters. You can do this afterwards as well, since it's really just doing the RBD cluster SOP, but it's built in here by default so that you can just get a good result right out of the box. On the detail tab, there are just a couple options to be aware of. One is the detriangulate option. Since this is Boolean based, you can select whether you want to detriangulate or detriangulate only unchanged and so on. And then for the proxy geometry, since this is Boolean based, it's rather easy to get very concave shapes. So there's an option built in to turn on a convex decomposition, and then you can control the max concavity that you're using for generating the proxy geometry from the third output versus the high resolution geometry. And then just looking at the constraints quickly, I'll turn off clustering for a second and also turn back off the guide geometry. So if we look at the constraints, we're also going to get a few primitive groups that we can use for targeting with RBD constraint properties and things like that. So we'll get some some constraints between the cuts that were made for the cut step as well as for the grains between our fractured pieces. Now that we've taken a look at some of the fracturing settings, we can also get back to looking at that fracture per piece option that I mentioned before. So instead of just having a single input piece of wood, let's say that we actually have a door frame that's made up of a few different pieces already. So in this case, we have 12 input pieces. So if I was to send this into RBD Material Fracture, it would by default just treat it as one giant object. It's okay with the object consisting of different connected components. But in this case, it doesn't really produce the look that you're looking for, because if we look at the exploded view, some of the grains are in the wrong direction for what we'd expect. What we really want is to be able to individually fracture each of those pieces and have, let's say, the grains be aligned in the right direction. Obviously, you could do this by just dropping down a for each loop and doing it yourself, but this option is built into RBD Material Fracture both to simplify the workflow and also make it a bit easier to control some of the random offsets and things like that, so that you can very easily get a bit of variation between each of the pieces that's being produced. So if we turn on this fracture per piece option, we'll see that we get a few new options that pop up. So we have the option to specify what our piece attribute is, of course. And then we have a single pass option, which just lets you easily isolate a single piece and tweak the fracturing settings just on one piece at a time instead of forcing you to continually refracture the entire geometry. And then we also get this random seed option, which we'll see in a second. So on top of these parameters that have appeared, we'll also get a few new parameters like this randomness setting for the grains, which let us vary up the settings for each of the input pieces. So I'll turn back off the single piece. And then if we look at the exploded view, we're now individually fracturing each piece. So the grain directions are in the direction that we'd expect. But then if we change around this randomness setting, we can get a bit of variation between the spacing of the cutting planes from one piece to the other. So they're not perfectly uniform. If they were set to 0, then we're getting kind of the same spacing between the cutting planes. And then as this increases, we'll get some pieces that have their cutting planes, spread fairly far apart, and then others that are pretty closely packed together. So this will appear for a bunch of the different fracturing settings. So on the cutting planes, we'll also see some randomness, an extra randomness parameter showing up here. And all of those are controlled by this random seed. So you can get a bit of variation very easily across all of the different fractured pieces. And the same goes for glass and for concrete, where you'll get similar randomness settings for any of the things that already have random seeds for them. Like in the case of glass, the number of radial cracks that are being produced. And so before we get into building a full example, there are just a couple of tips and tricks I wanted to mention for the workflow with using these multiple output nodes. So there's a couple of really handy shortcuts in the network editor that you can use, and I've been doing a couple of these all along, actually. So if you already have a node selected, and then you're in the tab menu and you pick the node that you want, if you do Shift-Enter instead of just pressing Enter, it'll wire up all of the outputs of the currently selected node to the inputs of the node that you're putting down. So this can be really handy for these multiple input and output nodes to make it really simple to wire them up in a sequence. And then along with that, if you already have the node that you've already put down and you want to wire them up, instead of just dragging each wire one by one and so on, which can be a little bit tedious, if you shift click on the outputs of the one node, so if I click on the first input, shift click on the next, and then shift click on the third, then they've been bundled up together. And then if I wire them into the first output, it'll distribute those wires in a row. So this can be really handy if you've already placed down a node and you just want to very easily wire it up to another node. And then there are also a couple of useful utility SOPs called RBD pack and RBD unpack. And the idea with these is pretty similar to the vellum pack and vellum unpack SOPs if you've seen those already in the vellum workflow. So if we take a look at this, RBD pack takes 3 inputs. So I'll just wire that up. And then what it produces is it just gives us a single output. So one piece of geometry, but it contains 3 packed geometry primitives. And so what it's done for us is it's taken the geometry, the constraint geometry, and the proxy geometry, converted each of those into a packed primitive, and then merged them all together. And then it's also tagged them with this RBD type attribute named either geometry constraints or proxy geometry. So we've merged all of the geometry together, but doing it with packed geometry primitives instead of just directly merging all of the geometry together. And this is really handy because the constraint geometry usually has a totally different set of attributes from the fracture geometry, and so we avoid having to merge together all of those attribute tables. Instead, we can just put each into a packed geometry primitive, leave it on its own, and then merge them all together. So now we just have one piece of geometry with 3 packed primitives in it. And so the nice thing with this is that if you do this, then a lot of things like switches and merges can be a lot simpler. So if I have 2 different fracturing setups that I want to switch between, let's say I had some different stuff going on in this branch, then I can just use a normal switch SOP and switch between them on demand, and then use RBD unpack to do the inverse operation, which basically takes the incoming pack primitives, splits them out based on the RBD type attribute that we had here, and then gives us back our geometry, constraint geometry, and proxy geometry again. So this lets you avoid having to duplicate switches and merges and so on for each of the 3 streams. And it's also nice for things like for each loops where you want to process different things in parallel and then merge the results later on. This can be a handy workflow. The other nice thing about this is that if you want to cache out the geometry to disk for thick geometry, constraint geometry, and proxy geometry all together, this can also be really handy. So you just drop down an RBD pack SOP, and then you can use a file cache SOP to just cache out everything together if you want to do that. So now let's take a look at doing a full example and also a little bit more about setting up constraints between the different material types. So in this setup here, I've got the full version of the wall geometry that I was using for the earlier demos. So I've got a name attribute already for the different concrete, glass, and wood input pieces. And then I've just got a sequence of RBD Material Fracture SOPs to fracture each of those different parts. So for the glass, I'm using the group field here to just operate on the 3 input glass panels. And then I've also got the fracture per piece setting turned on to separately fracture each of those panels with 3 scattered impact points each. So the settings here for the glass fracturing are pretty much just left at the default, and I've just left off the default constraint properties as well, because we'll set those up later on. So if we look at the guide geometry here for the constraint network, we'll see that in red, it's just highlighting the constraints that were produced from this fracturing operation. And the fractured geometry option is a little more useful now that we're using the group field, because it just highlights the pieces that we were producing from this operation. And then the wood fracturing is the same idea. I'm just using the group field to select the wood pieces, fracture per piece is turned on, and then I've just got some clustering turned off, and then, because I'm going to be using constraints instead, and then I've got the detriangulate settings adjusted a little bit, but otherwise it's pretty much at the default settings. And so again, if we look at the constraint geometry view, we'll see that in white, we have the constraints that already existed before between the glass pieces, and then in red, we've got all of the new constraints that were produced between the new pieces of wood. And then the concrete geometry is the same idea. So we're just operating on the single piece of concrete. And then I've also got the edge detail and interior detail turned on. So there's a useful option on RBD interior detail that's very handy to mention. So we'll take a look at that now. Or sorry, not on RBD interior detail, on RBD Material Fracture. So I'm going to start by just turning off the fracturing operations temporarily, and then I'll just wire this up. So if we select one piece to operate on, so let's say concrete 0, 0, and then I'll turn back on one level of fracturing and just create a bunch of pieces so it's obvious what's happening. And then we'll just turn on the visualizer so we can see which piece it was. So here we've got this one concrete piece, which we're just going to be doing some additional fracturing on by isolating it with the group field. So if we look at the constraint geometry visualizer, what we'll see is that in red, we have all of the constraints that were produced between the fractured pieces that got generated here. So we've just produced a bunch of fractured pieces from our original input piece. And so we've got these constraints in between all of those pieces. But then in yellow, we've also got constraints that were generated between the pieces that it was a neighbor with. So if you'll notice on the original concrete geometry, we had some constraints between this piece and a few of its neighbors. And so as this piece got subfractured into more and more pieces, the SOP will also update all of the constraints to the neighbors to point to all of the boundary pieces that got produced. So what this means is that as you continue to fracture certain pieces more, the SOP's able to update all of the constraints with its neighbors to reference the new pieces that got produced along the boundaries there. So this can be a really handy feature to take advantage of. And in fact, you can also use this for setting up intermaterial constraints. So let's take a look at that. So if we first inspect the constraint geometry that got produced at the end of this fracturing and look in the group visualizer, we'll see that we do have a bunch of constraints between, say, the wood pieces that got produced, the glass pieces, and the concrete pieces, but we don't have any constraints between the glass and the wood to the concrete pieces that they're neighbors with. So if we were to send this into the sim, it would just kind of fall apart. The glass might fall out of its window frame, for example. So one idea is to take advantage of what we were just doing with that single piece and use it to set up the constraints between the different material types for us. So if we go back to our original wall, what we could do is set up constraints between the original unfractured glass piece and the 4 wood pieces around it, as well as between the wood pieces and the concrete that they're originally neighbors with. So this is what I'm doing here. So I just have a blast stop to isolate the wood and the glass, connect adjacent pieces, and then I'm also setting up a primitive group called wood glass for those wood to glass constraints so that we can track them and easily identify them later on as they're subdivided and rewired to the new pieces that get created. And then the same goes for the concrete to wood constraints. Whoops. And then if I merge those together, we now just have some initial constraints between our unfractured pieces. So we have a few constraints between the concrete and wood to glass. So if I go back to the glass fracturing and take a look at the constraint network, if I wire in these initial constraints into the second input, we'll see that those also do get updated for us. So as we fracture these glass panels, it's also taken those original constraints between the glass piece and the wood pieces it's adjacent with and rewired them to all of the pieces of glass that got produced along the boundaries here. So we'd have both those boundary constraints that are being updated for us as the fracturing happens, as well as all of the constraints we get by default just between the glass pieces. And so we can recook the rest of the fractures and then take a look at what we get at the end. So now if we go back to looking at our constraint geometry, in addition to the wood grain and wood cut groups we had before, now we've got all of these wood to glass constraints that got created for us along the boundaries just based on those initial constraints that we had. So as pieces got fractured, it keeps updating all of the constraints along the boundaries of those fractured pieces. And then we also have our concrete to wood constraints too. So now we have enough to be able to fully constrain together all of these different material types. So this is one way of working if you want to set up your relationships between the different material types ahead of time. But you also, of course, always have the option of doing custom stuff afterwards. Like the output geometry from these constraints is just the usual constraint network format for bullets. So your name attribute on the points and your standard attributes like rest length and constraint name and so on the primitives. And so you could just take the fracture pieces that got produced, drop down connect adjacent pieces and do some stuff to set up those boundary constraints yourself, and then just merge it in with the constraints that you already got from RBD Material Fracture. So that's always an option. And so once we've finished doing our fracturing setup, we can then use RBD constraint properties to set up the properties for the different constraints that we're going to have. So in this case, I'm just setting up for the first level of concrete fracturing, which the guide geometry will show here. I'm just setting up some weak glue constraints. And then for the second level of concrete constraints, I'm setting up some stronger constraints. So we have kind of a clustering look. And then for the glass, I've got some extremely weak glue constraints so that it breaks very easily. And then for the wood constraints, I've got fairly strong glue constraints so that it takes a little bit more force to break them apart. And then also some soft constraints that take effect afterwards. And then finally, for the concrete to wood and wood to glass constraints, I've got sort of a moderate strength glue constraint. And so now at this point, we could take the geometry, the constraints and the proxy geometry and send that into a simulation. So now that we've got our fracturing and constraint geometry set up, let's take a look at a simulation to see how this all works. So a few of the RBD shelf tools, like the RBD objects shelf tool, were updated to understand these new 3 input and 3 output nodes. And so they'll be able to set up the constraints and proxy geometry and so on for us. So we're going to use the shelf tool and take a look at what it set up, and then inspect it a bit to see what was going on, and then make a few modifications for our simulation. So we'll use the RBD object shelf tool and select our geometry object. And then if we dive back into SOPs, we'll see that it dropped down a few nodes for us. So first up, it dropped down a null for our constraints that are coming out of the second output, and we've already got our attributes and everything set up on them from RBD constraint properties. And then from the third output for the proxy geometry, it's also putting down an assemble SOP to create pack fragment primitives from us, and those are going to be getting sent into the simulation as our collision objects. And then finally, from the high-res geometry, it's putting down a standard transform pieces setup. So it's using the DOP import SOP in the create points to represent objects mode to get a bunch of points representing the transforms from our proxy pieces, and then sending that into transform pieces to update the high-res geometry. And so let's go back into the simulation and see what it created for us. So it's a pretty standard bullet setup. So we have an RBD packed object DOP, which is fetching our proxy geometry pieces. And then on the bullet data tab, the one option that's turned on is the create convex hull per set of connected primitives option. And so this will be creating compound shapes from any pieces that had multiple parts to them. So this would be if we had like a convex decomposition that we were doing for our proxy geometry or something like that. And then it's putting down a constraint network DOP to fetch our constraints that we had set up. And then it's created 2 constraint nodes for us. So we have a glue constraint and a soft constraint. And the data names on these are set to glue and soft. And so these are matching what we were doing with our RBD constraint properties SOPs. So here we had been setting our constraint name to glue, for example. And so those need to match up in order for those constraints to be picked up. And then the other thing that is set up is all of the values for the constraint properties like rest length and stiffness and so on are set to 1. And so this ensures that there isn't any additional scaling that's being done from multiplying these values by the primitive attributes that we set up in SOPs. So we were setting up all of our properties like how stiff our soft constraints were, for example, in SOPs. And so this lets us do a completely SOP-based setup. And then finally on the solver, settings are all just left at their default, and then we have our usual gravity DOP. And so if we press play, we're going to see that the objects just kind of fall down and aren't really doing anything too interesting. So we'll need to set up some colliders. So let's set up a ground plane DOP first of all, but we'll see that once we press play, it just kind of collapses. So we need to make our structure a little bit stiffer. So one way we're going to do that is just by setting up some inactive pieces at the bottom, just so that the whole object kind of stays together nicely. So if we go back into SOPs, what we want to do is take our points that are near the bottom and set up the active attribute to set up those as being initially inactive pieces. And so we're just going to drop down a group create SOP and group the points by a bounding box. And then we'll just adjust this to grab some of the pieces that are near the bottom. And then once we've done that, we'll just drop down an attribute create SOP to set up our active attribute. So we'll just change the attribute name to active and then set it to use our point group that we just set up. And then we're going to set the values for the points in the group, which are inside our bounding box, to 0 so that they're inactive, and then leave our default as 1 so that all the other pieces are active. And so now if we go back to the simulation and take a look at it, we'll see that our wall is holding up pretty nicely. So now we need to set up some actual colliders to crash into it and make it do some interesting things. So I've set up this wrecking ball geometry here. And so it's just a sphere that I'm going to crash into the wall. So I'll use the RBD object shelf tool to bring that into the simulation. And then we're just going to set up some initial velocity to make it move quickly towards the wall. And then we'll also just set up the mass to be a little bit higher so that it's a bit of a heavier object. And so now if we press play, we'll see that we're getting some more interesting collisions now. And the wall is breaking apart pretty nicely, except that the wood is kind of staying together a little too strongly. Like we want to be able to have it break a little bit more noticeably. So we'll go back to the wood constraint properties, and first we'll drop down the strength for the glue so that it breaks a little bit easier. And then we'll also drop the stiffness a little bit so that it's bending a little bit more after it switches to a soft constraint. And so now if we press play, let's take a look at what it looks like. So we'll see now that the wood panels there are bending a little bit more nicely. And so we're getting some much nicer behavior now. So this just about covers what I wanted to do in this masterclass. So thanks for watching.